morning to everybody, ladies and gentlemen. As said before, I will I will provide you just an overview of research activities carried out at the Department of the University of Campania. So I work in a working group with 5 people, 3 full professors and 2 researchers. And so this is the overview of this presentation. So we usually work on a research framework that relies on 4 legs that are the ones you see in the presentation. So multidisciplinary design optimization, aerodynamics and aerothermodynamics, flight mechanics and guidance, navigation and control, and structural analysis. Today I will provide you an insight on just the first 2 items that are closer to my activities, of course. So, with multidisciplinary design optimization, we intend to provide to the scientific community a very interesting airship configuration that I will show you later, that are characterized by improved performance from hypersonic point of view. Okay, so that's good. Okay, so we usually use a very interesting mathematics that belongs on soft object modeling that are very interesting because provide very interesting shapes not yet seen before. So this is on the right side the classical state vector we use in our activities. So a classical design cycle where all disciplines are involved in terms of a multidisciplinary design optimization. So we work on shape parametric model, on parametric model for thermal protection system, on a trajectory model, and so on the thermal state of the thermal protection system for what concerns the design of this important subsystem, as you know. So this is, for instance, an example of a Pareto front that we usually use for the optimization. And in particular, on the right side below, you can see the interesting curve shape. As I said before, probably not yet seen so far. So we are working on these new shapes, and I will provide you some insight about that. So this is an example of the parametric model we usually use for the airship design. So we have a lot of parameters that we consider in the optimization process, and for instance we have a look also to the layout arrangement for what concerns the crew accommodation. So on the right side you can see possible arrangement for the people inside the ship. And this is another example of other parameters usually used for what concerns in particular re-entry vehicles, because as you know, we need in this case very blunt shape. So there are other parameters that distinguish the airship from the hypersonic cruise from the re-entry cruise, of course. So this is an example of our mathematics, as I said before. This is an idea. There is a movie, in this case, of course, the movie. Someone could help me, please?
Per favore date una mano a far partire il filmato.
In this movie I show you as we are able to move from a very simple shape like a sphere to obtain this shape on the right side. And this is possible. Wow. if there are problems, we can imagine to start the movie outside of the presentation if you want. There is in the folder the file. I prefer to show you this movie because it's very interesting. Okay, let's start this movie. I suggest to start the movie outside the presentation. Probably this way we can skip this framework. Okay. Okay. So you can see how we are able to move from a simple topological shape and comes from this simple shape, we are able to reach this arrow shape for both hypersonic cruise and hypersonic re-entry phase. Okay. And these activities is embedded inside our design cycle in a very automatic fashion. So the optimizer is able to provide us with, when we define the design constraints and requirements, of course, provide us the shape. These are another example of mathematics considered embedded in our design cycle that is based on soft object. That is another interesting way to obtain very nice shape that you can see in this other configuration. So we start from this shape on the left side that is a simple planform shape of the vehicle, and we are able with soft object by means of blobs to obtain the shape on the right side. So we are able to provide a sort of inflation of this planform shape to obtain the configuration on the right side. These are another example of our capability in terms of thermal protection design, because we have in this figure a sort of topological map of the vehicle. So each point on the map on the right side is a point on the configuration, and we are able to define the thickness of the thermal protection system in an automatic fashion during the design cycle, of course depending on the thermal loads expected during the re-entry phase or the hypersonic phase, of course. And these are an example of the results obtained by this topological map. On the left side we have the three-dimensional map, and the right side the results in terms of thickness over the vehicle configuration. Of course we have red, that means thicker parts on the leading edge of the vehicle that are, of course, the most solicited part of the configuration. These are another example of our capability in terms of re-entry phase. We see on the right side the re-entry trajectory in the altitude velocity map, and on the left side the temperature distribution evaluated during the design cycle on the outermost line of the vehicle, the left side, and on the cold structure of the vehicle. So we have at the same time evaluation of temperature distribution outer and inner the TPS subsystem, of course. This is another example of globes activities on thermal protection system. So the optimizer is able to provide us the right thickness of the thermal protection system, and as you know, this is a very critical item for the design because thermal protection systems are very expensive, are weight, and so it's important to use this subsystem on right side. These are how change the thickness all over the TPS of the vehicle. So this ends our capability in terms of multidisciplinary optimization, and I will show you just some other example of our conventional, let me say, activities in terms of aerodynamics and aerodynamics. For instance, you can see a typical launcher configuration we investigated. That is a classical hammerhead launcher with two strap-on boosters. We see on the left side the aerodynamics of the launcher for motor on and motor off condition, because of course this changes the aerodynamics of the vehicle, and on the right side a multidisciplinary analysis that provide at the same time full-field analysis and the dynamics of the booster at separation maneuver. This is an analysis in which we have a dynamic solver that calculates the 6-drop trajectory of the booster after the separation, a Mach 5 in this case. So these are other examples of capability in terms of pressure distribution and in terms of separation, bubble at hammerhead of the launcher, and the skin friction on the surface to have an idea of the shock-shock interaction that apply between the boosters. And as you know, this is another critical item for the design, because here you expect very high thermal loads. These are another example of capability in terms of flight regime assessment for what concerns the re-entry. On the left side you can see the several regimes coming from pre-molecular, transitional flow regime, up to continuum flow regime that the vehicle has to face during the re-entry, coming from about, in this case, 300 kilometers up to the landing, of course. And this is important for the aerodynamic assessment of the vehicle, of course. And on the right side, for what concerns aerodynamics, you can see the several re-entry trajectory in the altitude velocity map, where are provided also ISOMAC and ISO-Reynolds line for the assessment of the aerodynamics of the vehicle, of course. These are the example of classical configuration investigated at Vanvitelli, a classical wing shape configuration, and other example of fluid dynamic activities we usually do at the department. So these are the example. For instance, you can see on one side the ball shock that applies past the vehicle during a re-entry at Mach 25 and at 30-degree angle of attack. So you can see the trace of the ball shock in different planes, in different cross planes past the vehicle. Finally, this is the last example I can able to provide, that are results also about lifting body vehicles. We have on the left side an Apollo-like capsule, and on the right side a feasibility study we did about man-rated mission to Mars. You can see a classical lifting body that are needed for a manned re-entry on Mars, because as you know, the atmosphere of the red planet is very thick, so you must exploit as much as possible lifting capabilities of the vehicle to break in this thin atmosphere. Finally, these are the mock-up of vehicles we realized with 3D printing at the department, just to have an idea of this shape. And if someone is curious to see these vehicles, I have with me this shape, and I will be very like to show you this vehicle that we realized. Thank you.
Thank you, Professor Pezzella. The floor is open if there are questions, clarifications sought about this very detailed and clear illustration of activities carried out by the University of Campania. I see
what CFD tool do you use for flow simulation?
Okay, we usually use a commercial CFD code, but this code is upgraded with user-defined function provided by our side in terms, for instance, of chemical reaction system that are needed to consider at a very high speed condition for what concerns both re-entry in Earth atmosphere and Mars re-entries, because as you know, chemical effect. Because a very high speed condition, it is very important to take into account the chemical effect, because otherwise your solution is wrong, of course. So we use commercial code and user-defined function to provide to this commercial code particular feature needed for our simulation.
It's runs equations.
Runs equations. These are runs equations. Thank you.
Thank you very much. Thank you, Professor Pezzella. And now we'll just proceed and